It's my great pleasure to introduce Maryam Fazel from University of Washington. Maryam is head of the UW Squared Tripods Institute, which has a fancier name, IFDS or something like this. And today she's going to talk about policy gradient descent for control, global optimality via convex parameterization.
Thank you. Hi, everyone. It's a great pleasure to be speaking here, and I'm really enjoying the two-day visit to Cornell, and had the pleasure to talk to many of you. Really enjoyed it. So today I will talk about policy gradient descent for control. So before I start, I would like to acknowledge the collaborators on this project. So first, my student, Sun, who just graduated from University of Washington, and another recently graduated student from the aeronautics department, Jingjing Wu. These are students who worked on the project, especially Yue is the main author of the second part of the talk. And we also had collaborators, faculty from different areas, Ron Ge from Duke University CS, and Sham Kakade, who was at UW but has moved since to Harvard, and Mehran Mesbahi from UW Aeronautics. I'd like to first try and motivate the type of problem that we are going to look at. So policy optimization methods that optimize a policy or work directly by solving an optimization problem on policy parameters, and we will see what that means, are quite popular nowadays in reinforcement learning. RL stands for reinforcement learning. So in RL, or reinforcement learning, or deep reinforcement learning, where deep neural nets are used to parameterize policy, the policy optimization methods have been really popular and successful. They have shown really astonishing and impressive success in a variety of applications empirically. For example, in things like robotic hand manipulation, control of a robotic hand, and actually I'll show several examples of that, as well as things like playing games and actually managing to beat humans in very complicated games. An example of which was first the Atari game that DeepMind had a RL method that beat human players of Atari. That was in 2013. Next, the one that probably you have all heard in the news about was in 2016 for playing Go. So in terms of how impressive they are and what they have achieved, it's really interesting. So the 2016 Go playing code and tool was able to beat the best human Go player, Lee Sedol, in a round of 5 games, and the algorithm won 4 of those. So there is one time that the human won, so there's some hope for humanity, but that was an impressive thing. And then OpenAI recently also had a robotic hand that is manipulated, again, by a deep RL algorithm, and is able to solve a Rubik cube. There's like very impressive videos online that you can watch for these. So here's a dexterity, like learning the dexterous hand moves, and that one is a game playing. They're all solved by these methods. But these methods, so far, mostly lack good theory, like a good understanding in terms of optimality, convergence properties, or more or less statistical properties, samples. There are some very special cases studied and known, but pretty much, by and large, they lack a good theory. So this is the motivation for our study. We noticed that even for simplest problems of much better understood field of control of dynamical systems, if you look at systems whose dynamics are linear and, for example, costs are quadratic, which is the basic simplest problem in control, still understanding these methods in that context is not fully done. So that motivates our exploration. So I talked about control of dynamical systems. Let's also take a look at how people in the field of control think about problems of this kind. So in control theory, usually the goal is to design feedback policies in a continuous space that would control a system in various senses. So for instance, you have usually this kind of block diagram in the feedback paradigm, where you have a system that has a state xt, it could be an n-dimensional vector, with input ut and output yt. The output is what is sensed or measured and goes back to this block called feedback controller, which generates the control input that is fed back to the system. And you would do this for multiple purposes. So the goal would be design this block, design this feedback control block for different goals and purposes. For instance, you can say, I need to design the controller. Controller here is the same as policy in RL. We need to design the control or policy that would observe the Y's and set the control input U in order to, for example, stabilize an unstable dynamical system, so achieve stability. Or you may want to achieve tracking, so so that's for navigation, for instance, track a given trajectory, make the system follow a trajectory. Or you may want to optimize performance. Usually performance is specified in terms of gain of the system from some input to some output. For instance, D of t usually is a disturbance, that blue one up there, and you want to control the effect of disturbance on a desired output like this Wt, and you can also write that down as a performance metric that we want to minimize effect of disturbance D on W. So all of these lead to different problems in the field of optimal control and robust control. And historically, this field has had vast success, especially since 60s in aircraft control, in aerospace, in industrial and mechanical systems, industrial control, and network systems like power and energy networks, and many, many other systems. So our goal here is basically kind of looking at both these fields. We want to understand policy optimization methods that, in order to really provide some understanding and theory for these complicated RL applications, but in order to get there, we need to first focus on simpler contexts. So the simplest would be a classical control problem setting that we will look at next. And we want to also focus on the simplest form of these algorithms. So for policy gradient methods, or for methods based on policy optimization, there are many such methods. But you would like to, for example, start with methods that just take the gradient of the loss with respect to policy and update the policy. We will see examples of it. And then we ask this question: can we give any guarantees for policy optimization methods in learning feedback control policies? So the goal is to learn the feedback control, to find the best policy, find an optimal policy in some sense. And we want to do it by gradient descent on some loss function or cost function. And when would this work, and can we do it? An interesting facet of this, by the way, is model-free versus model-based views. And by that we mean, in the RL setting, typically people try to avoid fully modeling the dynamics of their system, usually because it's very, very complicated. For example, the dexterous hand with the Rubik cube. You can imagine that fully mechanically modeling everything is very difficult. Usually the environment in which such systems are operating is also hard to predict and hard to model. So they prefer to do only minimal modeling, but then rely on whatever measurement you're making from that system in order to make the update to the policy. Whereas, for example, in the control theory settings, the more prevalent view is model-based, meaning that there's attempts first to try and model the dynamical system, find a model for it, and then use that model in order to design the policy. And so there's debate about these methods, but actually at the end of the day, this talk is not about which method is better. At the end of the day, you really want to know both and to understand both of these, because in realistic setting, you want to be kind of partly model-free, partly model-based. So both are important methods. There's no reason to focus only on one. But one motivation for RL folks to not try to model is that those applications are just too complicated. They want to avoid as much as they can to do the modeling of the system. So what will we do is to employ sort of a modern optimization perspective here. So when we look at policy gradient descent methods, we are going to view them as first-order optimization methods. And I'll make a comment about zeroth-order Oracle methods as well, but the talk is not going to so much focus on zeroth order. It's mostly about first order, because that's actually the prevalent sort of method. But both first order and zeroth order are. All right, so with that goal, let's try to define things a little bit more systematically. So what is gradient descent on policy, or policy gradient descent? By that we mean methods that would iterate on the policy. What is policy? Policy is a mapping from the state to action or the input. It's exactly in the control theory setting is exactly that controller block. Let's denote it by K, and we keep it abstract for now, but we will see that in a concrete problem we're going to study, it will be a static matrix. In some other problems, it could be also a dynamical system. Okay, so K is the thing we want to design. You can think of it as a matrix for now. And we would like to use a first order oracle, meaning gradient of some cost function or loss function, and use that to update the current policy. So basically the methods are simply going to be the new policy is the old policy with some moving in the negative of the gradient direction with some fixed step size. That's the simplest possible algorithm. So we are interested in studying the algorithms of that kind. So we will show you what these losses are and what the control or policy parameterizations will be in some examples. But why is that interesting? Why is this simplistic method interesting to study? First, because people in reinforcement learning tend to use this style of method, mainly because they're very easy to use and easy to implement. And you can do many variations on it. As we know, first order methods have lots of variations. There is well-developed first-order optimization theory that one can draw on. We have tools that we can use that come from optimization theory that we can apply here. And also, after we understand the first-order method, meaning if a gradient is given to me, I know what happens, then I can also ask the question, if gradients are not given to me and all that I have access to are function evaluations, that will get us to the field of derivative-free or zeroth-order optimization, then what can we do? And in fact, we can actually show for very simple versions of derivative-free methods that the ideas from first-order methods sort of extend, at least in a very simplistic manner. So understanding first-order methods will also enable us to later look at the sample-based and derivative-free versions. And these derivative-free versions are actually closest to model-free RL approaches. So what are the key questions? First, we want to see when does gradient descent on policy converge to the global optimal solution. So the K star that minimizes our loss, let's say the global solution, that would be our best goal. And if that convergence happens, can we understand how fast? What is the rate of convergence? If the gradients are not available and only samples of the function value or the loss function value are available, what can we do? And these questions would be not too hard if the problem is convex. So if the loss function is convex in these parameters. But when things are non-convex, this can be very, very challenging. Why is that? So just to, everybody knows here, but just to give you a picture, a mental picture. If you're doing gradient descent on a convex landscape, from any initial point you converge to the global solution. That's a well-studied analysis of first-order methods in smooth convex optimization. We assume smoothness as well. And then if it's non-convex, you can have these like hills and valleys and so on. And of course, the point you converge to, or even like the manifold you converge to, will depend on the initial point. So in this simple example, different initial points go to totally different places. And these can have different values. So things can get very complicated. So we will be looking at a specific problem in which the L of K is not a convex function, but we will rely on other properties of this function to actually manage to talk about global optimality. But it's not trivial that if you have a non-convex function, you can say anything at all about the globally optimal solution. So before we do that, I'll take a look at sort of a broader set of literature about learning and control. So papers that basically looked at controlling, designing policies, but also learning at the same time. And it's not really a new topic as it might appear when I show things that were in DeepMind and very recent. The topic itself is not new. So it goes back to, for example, early 90s. There's work in the field of adaptive control and online adaptive control. Online adaptive control, in fact, is very close to this RL setup because you are obtaining samples from your system as you go along and you're adapting your policy accordingly. So there had been classic results in that field, mostly only asymptotic, nothing about rates or nothing about finite time or finite sample. There is also learning-based methods that were called neurodynamic programming. A book by Bertsekos and Tsitsiklis is on this topic. Multiple other approaches, adaptive dynamic programming and reinforcement learning, and even study of regret in adaptive LQR. So there are all these resources up until more recently. I have highlighted a couple of the works here. This one in bold by Moritz Hart, Ben Recht, and others is about just identification of a system, not designing policy or control. But one reason I highlighted it is that in spirit is similar to the work we do in the sense that they are looking at a gradient descent on a non-convex problem. However, it can be shown under some conditions that this problem can be quasi-convex, in which they give guarantees about learning the system, learning the dynamics. So in the sense of giving an analysis for a gradient descent-based method, it's similar. Also, there are other recent and very interesting work that take a different approach, where they go based on methods that are more closer to the traditional control approach, which is let's first learn a model of the system as best we can, and then use that model in order to design the policy. So work of Sarah, who's here, is one of those. And it actually sets up a coarse system ID problem followed by a robust control problem, which is able to achieve a good convergence rate and a good sample complexity for linear dynamical systems. And there are several other papers on different approaches of that kind. There is also approaches that are based on, again, learning dynamical systems with different, for example, spectral filtering approaches, closer to CS theory type approaches. And that some of this will also has been extended to the LQR problem. We're going to say what LQR is. It's linear quadratic regulator problem. I first used the acronym before giving the actual problem. And finally, this last paper here is actually from the controls community, and it's about designing controllers but with further constraints. So you want to design structured control. And this problem is very non-convex, and they solve it still by gradient descent. They observe so this work is actually very empirical. They observe good convergence to good solutions, but there is no theory about when this convergence happens. So this is basically the landscape of types of results available, and this is kind of a set of very different style of approaches. Some of them focus on learning a model before control design, and some of them focus on learning the control policy as you go along. So. But all combine control and learning. By the way, if you had any question, feel free to interrupt at any point. So in the rest of this talk, I will set up one concrete control problem, the linear quadratic regulator, and we'll talk about its properties. We'll set it up as a loss function, as a function of k, the policy parameter, and we show it's not convex, but we show that something that might at first look surprising is gradient descent actually does converge to the globally optimal policy because of other properties this problem has. This relies on two very special properties of this problem. One of them is coercivity of the cost function, meaning, so we'll see what that is, but the more important one that we're going to focus on is the second property, the Polyak-Lojasiewicz or PL inequality. That sort of relates the value of your gradient to how far you are from the optimal solution. So the suboptimality in the loss is connected to the norm of the gradient, and that allows very strong properties. Then we'll talk briefly about how this approach can extend to more complex control problems. For example, there is work that has extended these to robust control, to linear quadratic games, to Markov jump systems, and to linear quadratic Gaussian problem where you have partial observation of state, which is a much harder problem. There exist some partial results for that problem. And then finally, I would like to show that the PL property, that's a key property that makes the LQR analysis work, actually is connected to convex parameterization. Some alternative parameterization of this problem that happens to be convex in a different space with respect to different variables. But we'll see how that helps us show something about our original non-convex problem. Any questions so far? Okay, so linear quadratic regulator has a long history. This is Rudy Kalman. He was one of the first people who worked and actually contributed a lot to the, of course, theory of Kalman filtering and this particular problem, linear quadratic regulator. And here is receiving the Medal of Science, National Medal of Science from President Obama in 2008. So this problem is in the continuous time case, you have a state vector, and this is the derivative of the state vector equals a matrix A times the previous state plus a matrix B times the input. So that's the model. That models the dynamics of how the state xt is evolving when input ut is applied. And you start from some initial condition, x0. And so the question is, how do you design this ut, the input, so that some cost function of the state is minimized? The cost is defined this way. So we want to pick an input signal or input sequence, u1, u2, u3, etc., or in the continuous time, a whole continuous signal, such that its cost, which is the integral of 0 to infinity of xt transpose qxt, so a quadratic function of the state value, plus a quadratic function of the input, integrated over all time, is minimized. So that's something we want to minimize. Now this expectation over x0 is because we are going to look at a case of LQR where the initial condition x0 is chosen randomly. And for simplicity, we choose it from Gaussian distribution, zero mean with a variance sigma.
So,
Yep.
a very naive question, always surprised me. Why is this a good objective function? Why does it make sense? Like linear constraints make perfect sense, right?
Mm-hmm.
But why this particular quadratic function?
Yeah, that's a very good question. So in some sense, these quadratics measure the energy or norm of a signal. And the norms are defined by these fixed matrices that are given. So you can shape the norm. So L2 norm in general captures the energy of a signal. And for example, this would be energy of the input. I want to control the state to go to my desired state. Usually desired state is 0, by the way. The way it's written here, it means that we are steering the state to 0. So this is making x small to go to 0. But it's also making it such that it's over the whole time its norm is small with respect to matrix Q. And this says that we do not use a very big input. So input is usually costly. If you apply very large inputs, you can push your state to 0 fast, but it costs a lot. So you're balancing how much you're... Right. How much you're pushing your state to 0 and how much it's costing you in terms of the input.
So, excuse me, this will be an open loop control? You're assuming that X is not observed?
No, we are going to actually look at closed loop. So we're going to design, actually I think it comes up here. We want to design U as a function of X. And so it turns out for this problem, the solution is actually a static state feedback. So optimal ut is a matrix K times xt. It's a static feedback.
So if you didn't have that expectation, this becomes completely classic. But I'm confused about the expectation with respect to the initial.
Yeah, the expectation is not playing a very big role except one thing. So some initial conditions will be bad. From some initial conditions, you cannot drive to 0. So you want to just avoid that. This expectation avoids it. Or you can equivalently say, I want to minimize this cost over a set of linearly independent directions in the space. So take the summation over a set of linearly independent. So that actually captures the overall general behavior without worrying about whether a specific initial condition might be a bad one, where the cost cannot be reduced. So we want to make the cost independent of initial conditions. So just for simplicity, an expectation with respect to the random Gaussian x0 is not that big a deal because it just goes into the first step and then your dynamics goes from there. Yeah, it's actually typical in control to define it this way. Not always, but for simplicity, it's easier to define it this way, and then not require any condition on x0. So for this particular problem, it's known that the optimal solution is actually fully well known, and you can write it down as an algebraic equation, as a solution to an algebraic equation. Stabilizing policy, by the way, means that you are creating a trajectory that goes to 0, and therefore the system that is stable. So this is now the control policy because it's relating our state to input. So input is a function of the state that you observe. By the way, we are observing the full state in this problem. The xt is fully observed. So it's known from, thanks to Kalman from 60s, that this is the solution. So some matrices times x with a p matrix over here, where the p matrix solves this equation written here, which is called the Riccati equation. So it's a nonlinear equation in this variable p, but there are nice linear algebra methods for solving it, and the solution can be obtained. There are multiple methods. Once you solve this equation and find p star, you can plug it in the solution in the equation above and find k star. So this is the classical way of solving the linear quadratic regulator, but you would need to know your A and B and Q and R matrices to solve these. Either that, or you need to have a way to quantify if your A and B and Q and R are very unknown or uncertain, then how would the solution of the, so basically do a full perturbation analysis on the Regulator equation. But we are interested in looking at policy gradient descent, so let's remind ourselves what that is. So we wanted to design this feedback controller. We denoted this by, in this problem setting, by a matrix K that corresponds to this block. If I find K star, I have designed the optimal feedback controller or the policy. And the landscape of this problem as a function of K. So once you actually plug in K into the cost function, we didn't do that, we just wrote the cost in terms of X and U, but once you do the recursions and plug it back in, it's actually a non-convex, very messy function, and its contours or sublevel sets look something like this. So question is, does gradient descent on this function converge to the globally optimal policy? Let's say that's the star here.
Question here, because on previous slide, I mean, that the solution, is this for general, or is it additional condition on this dynamical system, or is there no more condition on anything? Because I'm worried that if, what if for the, under no control, this dynamics will go, diverge, go to infinite, does not go to zero.
I don't think there is any other condition needed. Is linear dynamics? R should be invertible. Yeah, I mean, R should be invertible. I think Q, let's say R and Q are positive definite. That's one thing.
Yeah.
R and Q positive definite, but A and B, I don't think so. Is there any, maybe observable?
Wonder if the worst case, maybe that cost is always infinite.
Yeah, so with bad initial conditions, that could happen, but we avoided that with this expectation. Yeah, I actually don't think so, but we can always check if there is any other condition needed. Yeah. That's actually classical theory, I should know. It's like taught in control courses. Yeah. Okay, but so yeah, we wanted to see what gradient descent does. So gradient descent for this problem was first actually studied in our paper in 2018. You might be surprised how come people didn't study this before. Isn't it like obvious? Well, they didn't because they noticed this problem was non-convex, and they had this other algebraic approach, so it didn't seem there was a need to do that. So if you do have your ABCD matrices, there doesn't seem to be any need to worry about the non-convex cost as a function of K. So first of all, we check that this cost function as a function of policy is not convex, or quasi-convex, or star convex. These are variations of convexity that are still nice type of structures for which one can actually solve. They're not too far from convexity. They can basically be done by convex optimization. This L is not, does not have these properties for dimension bigger than or equal to 3. So if you look at dimension 1 and 2, actually it happens to be convex. But dimension 3 and bigger, no longer. It's interesting. We can show this by creating counterexamples. So for example, it's actually not too hard to show counterexamples where you have two controllers, K1 and K2, both have bounded LKs. So LK1 and LK2 are not infinity, but you take the midpoint, then L blows up to infinity. So that quickly rules out the convexity. And also the quasi-convexity, etc., all of them. Another property we showed was that the loss as a function of K blows up to infinity as K approaches the boundary of the set of stabilizing controllers. So stabilizing controller means that any controller for which the closed loop system has all of its poles in the left half plane. So the overall closed loop system is a stable dynamical system. And that set is non-trivial because, as you can imagine, has to do with eigenvalues of A minus Bk matrices. But Lk has this property that it goes to infinity as K approaches the boundary. And the niceness of this property is that you don't need to really worry about that nasty boundary. If you are starting inside the feasible set, your gradient descent is such that it's trying to decrease the cost, so it never will go towards the boundary. So this is called coercivity of the loss. The second property that's actually really, really important and makes everything work nicely is the PL inequality, or Polyak-Lojasiewicz inequality, which in general is written like this. It says that if your function satisfies that property, if the norm of the gradient L2 norm of the gradient, or if it's that's it's L2 norm, is lower bounded by some constant c times the suboptimality in terms of the loss with respect to the optimal controller. So k star is the true optimum controller. Raised to some power alpha, this is the most general version of the inequality. Then you can talk about alpha 0 or 1 or 1/2. A particularly interesting case is when alpha is 1/2, which equivalently means that norm gradient squared is lower bounded by the suboptimality gap, which then immediately, with like 2-line proof, shows that gradient descent will give you linear convergence. So this property with alpha equals 1/2 directly gives linear convergence, and that is well known. So once we show these two properties, basically we are done. We can then say the policy gradient descent converges to k star from any stabilizing initial k0. So this condition means that I'm starting inside the feasible set. If we do not have an initially stabilizing k0, there are other auxiliary methods to try to find one. There are some papers written on how to do that by, for example, sampling from your system or tweaking the system first and getting k0. So it's not too expensive to get an initially stabilizing k0 based on those rules. But once you have that, you have a convergence to the optimal policy by gradient descent with a linear rate. And also this analysis extends to related algorithms, for example, natural policy gradients, which is a variation on gradient descent with a sort of a normalizing matrix in front of the gradient. Question? Yes.
This PL inequality, it looks like it's pretty much the same as Lipschitz continuous. Is that true?
It's different. I mean, it actually shows something much stronger than just Lipschitz. It is basically saying if your norm of the gradient becomes small, as you're making the norm of the gradient smaller, you have to push LK to LK star. So norm of the gradient is really pushing you towards optimality, so much stronger than just Lipschitz.
I think we have a hand in the Zoom as well.
Oh, please go ahead.
Yeah.
If there's a question on Zoom.
Hi, so I'm not sure if I understand this. So you just update the gradient and check the difference, and if the difference is small, then what happens?
Yeah, so simply the updates are simply like this. The update is just move with a fixed step size in the direction of the negative gradient. And it converges to the optimal k star with a linear rate. Yeah.
But it's not convex, so...
Yeah, it's not convex.
So how does that work?
Because of this. The magic is all in this one. The PL inequality. This is a very unusual inequality. It does not hold for too many functions, but it happens to hold here. Whenever it holds, you're good. Yeah, it is
imply
unusual.
that it's locally convex?
Well, because we said with respect to all k with respect to k star, it actually means that it's holding globally. For a lot of problems, if people are interested in local convergence rates, they can use a local PL inequality, but this one is global.
All right, thank you.
So the magic is that this particular L function has a lot of nice structure. Yeah, question?
Does this require the system to be controllable?
Yeah, I think that might relate to the question that was asked earlier. Let's say it is controllable so that we are not making any mistake. It may not, because we avoided those bad initial conditions. It may actually be okay without stating that it's controllable, but yeah. Let's say it's controllable to make sure we are correct. Okay. Here's a simple numerical experiment. This was a very small system, but you can actually see that the convergence, not only in LK, this is convergence in K itself, K minus K star divided by K star, is actually linearly converging. You see the linear convergence. And that you can also see that the contours or the sublevel sets looks like this. They're definitely not convex, at least for sure closer to the boundaries. So the full theorem would be something like this. I won't go into the details, just to show you there's a big constant in front. This is the linear rate that says that the number of iterations in order to get epsilon close to K star scales as log of the initial gap divided by epsilon, so log 1 over epsilon rate. But there's a big constant in front that, not that the value is big, I'm just saying it's a complicated constant that depends on all sorts of things in your system, the norm of the matrix P, the norm of the, this is the initial covariance, so covariance of the x0. So we picked x0 initial state randomly, its covariance is sigma 0. I think in an earlier slide I used omega, that's the same thing. Right, so there is these problem-dependent parameters that show up in front. This one, the top one, is for natural policy gradient, which is actually, the expression is a little bit simpler. For gradient descent, the coefficient is messier, so I haven't written it down, but you can look it in the paper.
Can you remind us what R is, capital R?
It was the U transpose RU, the part of the cost that penalizes the input.
Oh,
R
so
is the matrix that penalizes the input.
So, okay.
Right. It's a little bit hard to interpret the constants, but you can see the details in the paper if interested. So I'll just mention this as an aside, because the rest of the talk is also more about gradient descent. So far we were assuming exact gradients, and we're going to kind of stick to exact gradients. But what happens if you don't have exact gradients and you only have function value axis? So your oracle is a 0th order oracle, or you're in a derivative pre-optimization setting. Then you will basically use those evaluated loss at different k's in order to estimate the gradient. Let's say you get a big L hat, gradient hat. And then we can still do the rest of the analysis. So this is helpful. This approach is helpful if you actually don't know or don't want to directly learn the A and B matrix, but you have access to other ways to evaluate the cost at every point. And this is actually a situation that's very close to what's realistically happening in RL. At the current policy, you can, for example, perturb the current policy and see what happens to your loss. And it's called rollouts. You roll out a new policy for some time, you gather data, and then you use that to make a policy decision. Or sometimes people have simulators, etc. So there are ways to evaluate the cost, but you do not want to estimate A and B. Then this approach will be helpful. In this approach, there is basically an exploration that happens when you, for example, add noise to your current policy and evaluate how much loss is incurred in those rollouts. Yeah, you can basically, for example, use very, very simple 0th order optimization that only evaluates at one single point, or do some fancier ones that evaluate at multiple points and things like that. But we won't go into that very much. So these methods would converge to global optimum following from the analysis of gradient descent with enough samples. Samples are actually much more than one would. So you need a lot of samples to make it work, but we can quantify exactly how much. At least for the very simple method of one-point evaluation, is fairly high number of samples. Then there are improvements on this that were made by others. For example, you can use 2-point estimates and other more fancy derivative pre-optimization to improve the number of samples, but still in general in these methods it's higher samples than, for instance, learning a full model of AB first. And so this part of the analysis also extends to natural policy gradient methods, a bit more general. Then, after we had that paper in 2018, there was a burst of research interest in this style of problems. And there were a bunch of different problems that were similarly studied by policy gradient and shown that policy gradient, this updates on the gradient, will converge to the optimal policy. This includes, for example, continuous LQR, which I just showed you, then discrete time LQR, which needs a little bit more work. Our original paper actually did the discrete first and then the continuous came after. Robust control, H-infinity control, there are some results for problems of that kind. Structured finite horizon, LQR, decentralized control. Decentralized control under additional assumptions that makes the problem nice. In general, decentralized control can be very hard. So these papers all showed the same thing, that still you can do gradient descent on K and get the best policy. There was also results on LQ games, linear quadratic 2-player games. So it's a game version of 2 players having linear dynamic and quadratic cost. Markov jump linear systems looks much more complicated, but still the same thing holds. I'll show this problem towards the end. So each of these papers actually developed a method specific to that problem basically they were showing coercivity and they were showing something like the PL condition, and sometimes they did it in a slightly different way, but each has a handcrafted analysis. Some of them are pretty complicated. So one question that came up was, is there actually something in common between all these problems that, at least from the point of view of the PL property, can we see why these work? Especially since that PL property is not a very usual property that arises in too many functions. Why does it work for all these problems? So essentially, can we connect the PL property, or desired property, to convex parameterization? So the key or observation that what's in common between these problems is that they all have a convex parameterization in a different space. So we'll say a little bit about how that could help. Here's an example for LQR. The LQR problem has alternatively this convex parameterization. Oh, I forgot to write down what this A map and B map is. These maps are actually called the Lyapunov map, and it's nothing but this thing, AP plus PA transpose, is called A of P, the map A of P, and it's also known as the Lyapunov map. And the same thing for the map B, that's exactly the same map applied to matrix L. So here we are introducing two new matrices, L and G. These are different variables. And the problem can be written as this semi-definite program, where now G has to be a positive definite matrix. This block matrix, ZL, L transpose G, is positive semi-definite. This linear equation holds between L and G, and this is the covariance of the initial state that is known. And the cost function will become a linear function of G and Z. So it's going to be trace of QG plus ZR. So this is a known derivation, but we're not showing how we derive this, but this is equivalent exactly to minimizing the LK, subject to K being stabilizing. So in summary, it can be written as minimizing a function f subject to constraints S, where function f and constraints S are convex. So for LQR, we can write it in this way, and the assumption that we have is the set is convex, the function is convex, bounded, and differentiable on S. So this holds for LQR, but also holds for all those other control problems, that they do have nice convex parameterizations. So we can observe, by the way, this problem is convex in L, G, and Z. And by the way, Z is an auxiliary variable that we need to set up this LMI. The actual variables that will be later used to extract the control policy from are the L and G. So with that assumption on convexity, so if I have a form of our problem where the problem has a convex cost and a convex constraint set, and we need further assumptions. So it's not enough to just have a convex reformulation or convex parameterization, but also there should be a link between parameters in the convex space and the non-convex problems parameters, the K that we are interested in. So a simple assumption would be that there exists a bijection between these two spaces, such that the cost function value is preserved. So for example, in the LQR problem, this is exactly the bijection. The K is always linked to LG inverse. K is equal to LG inverse. So if you get any L and G that's feasible in the second problem, you can get a K that is feasible for the first problem. And as long as the minimum value or the value of the objective, minimum value of the objective is also equal, you get a bijection between these two. So you get a bijection and this additional condition that the cost is preserved. So this is by itself, by the way, a strong assumption. Not all convex parameterization in another space may not have such a nice mapping with the original space. Another assumption can be written this way. This is actually basically the same. It says if you add the constraints that K equals LG inverse, that the value of this new optimization problem with this constraint is just L of K. And this should hold for all K, by the way, not just K star. So the L of K has an equivalent representation like this in a convex space with this non-convex constraint to the original K. And more generally, such analysis can be, or such assumptions can be repeated for settings where the mapping is not as simple as LG inverse, but any map that maps the new parameters to the original and that this map has nicely behaved first-order derivatives. So we leave it a little bit vague, but essentially for nice and smooth maps, which can be quantified, this analysis would hold. It doesn't need to be an exact bijection of the form LG inverse. Okay, so after this, what do we get? We have that the initial problem is the one on the left, so that's the non-convex one. We want to minimize over policy the loss function such that the policy is a stabilizing policy. Stabilizing, by the way, I probably didn't discuss it for those of you who don't know control. I didn't describe it a lot, but what it means was that the closed loop system is stable, so the state of the system goes to 0. That integral from 0 to infinity does not blow up. All of these are equivalent. And that basically, that was the condition that made the set non-convex. And for the LQR problem, that set is also the domain of definition of our function. That follows from that coercivity. And so that's the non-convex problem. This one is the convex problem in new parameters, the new L and G that we introduced, such that the K was going to be equal to LG inverse. And by the way, G was always invertible because G was positive definite, so it has never 0 eigenvalues. And the Z was the auxiliary variable that we just needed to form this LMI, linear matrix inequality. So once we have these two problems, under the assumptions 1 and 2 or 1 and 3, so 2 and 3 basically are alternative assumptions, we have the following, this very strong property that any point that makes the gradient 0 is optimal. So yeah, so that's why this problem actually works. So more specifically, we can also give rates of convergence to that optimal solution. If the loss function is just convex, or the f function, which relates to the L function, is convex, then you get, this just hides a constant in front. So then you get a rate of convergence that is superlinear, and if it is strongly convex, you get rate of convergence that's linear with strong convexity parameter mu. So this part is kind of known, it just follows. It really follows from the structure of the problem, so that's the message. Tilde inequalities are hiding some instance-dependent constants that depend on the system parameters, like the ones we saw earlier, like the big expressions that had norms of the matrices in the system, as well as it depends on the initial point K0, the initial policy you start from. So it has natural dependence. We can write them out. If you look into the paper, there's actually details of this.
So, okay, the previous slide, that's a generic. This is it for your particular setting, or you are stating the general. This theorem is general, or it's a particular setting in your ALQ.
General under these assumptions.
Under these assumptions.
Right. This connection between these two problems, one of these, 2 or 3, is kind of key. So not only there exists a convex problem that gives you the solution to the original, but actually the basically feasible sets also map in a bijection. So you can think of this as, in some sense, go ahead.
So right, basically it's some F has some strong, nice convex property, then convert to original problem has this PL property. That's right. You can even think of it as, let's start from the convex problem, and you're going to reparameterize it in a way that makes it non-convex, basically. You start from a convex setting, but you write the variable in terms of new variables that makes it non-convex. If that mapping is nice enough that you don't really destroy the nice structure of the convex. So yeah, something like that.
So you were saying, sorry, on the next one you said if F is convex, you actually said superlinear convergence, but I assume you meant sublinear.
Sublinear convergence,
right.
Sorry.
But how does it, because I mean, it's not PL condition then, it's something else.
It's the PL with alpha equals, I guess the one that had alpha, there can be 1 or 0 or 1/2.
Okay.
1/2 is this one, which is the more famous.
Yes, it's the square, right, okay,
Right,
got
right.
it. So if it's just 1 then, I guess.
Right. So these statements really just follow. So the key thing is basically this from the previous assumptions.
Okay, right, so you have this, yes. I always think PL is the square.
Yeah, that's right. And that if the function, if the f function, the function in the convex problem is strongly convex, you get the mu really just follows from known convex, strongly convex results. Yeah, proof sketch. Maybe I will not go into the details, but yeah, basically you are kind of constructing a mapping between a non-convex space and a convex space, and then looking at the gradient of two different functions, but they're related to each other. So you are mapping a point kt from in the non-convex space to a point in this space, which is convex, L and G and Z. This was G, sorry. And then looking at the gradient at these points, and then the direction in which you move. So direction between the current point and the optimal solution gives you some information about which direction you're going to go in the non-convex setting. And all these can be linked to each other to exactly give you the relation between the norm of the gradient and the suboptimality gap. Let me skip these. These are some more details. Another sort of things that are interesting to point out is that, for example, I guess I call it G and P, sorry. G and P are the same thing. When is it invertible? When is this G or P invertible? And it turns out that the G will always be invertible if the initial x0 has a full rank covariance. So then the convex form will always be a positive definite G. And that the other thing is that the sublevel sets of the function are always bounded, so we can write down our constants that appear in the rates in terms of the sublevel set parameter. This is actually fully written out, those parameters that show up in the rate. So for example, the C1 that appears in this rate will be of this form. Yeah, I'll skip the details. Let me just tell you that there is other more complicated problems. So this was all about this LQR problem that might appear very simple. But it also works for discrete time LQR, by the way. And for discrete time, which is like this, so state at t plus 1 equals state at t plus b ut. And then your cost is going to be a sum instead of an integral, with similar condition of x0 being a random Gaussian vector. There's a convex formulation. It's a little bit more complicated. It looks like this. But again, the L of k satisfies PL with a similar argument. And I just wanted to show a much more complicated problem, and this is from another paper, not ours, work that came out after, which actually showed the same analysis for a more complicated Markov jump system. So here you have a linear, discrete time linear dynamical system with a random jump parameter, this WT, where the jumps happen with some probability. So if you're state I, there's a probability that you will move in the next time step to state J. And we can rewrite this whole control problem for that system, including all the jumps. So then the controller is going to also be piecewise like this. There's a K sub WT. And interesting thing is that there does exist a convex parameterization of this problem. It's this big problem now, but it's a semi-definite program. And similar reasoning does apply, and we can conclude that this also satisfies PL. I called it gradient dominant here. So when PL with a power 1/2 is also known as gradient dominant. It's another name for it. This one is another example, but let me skip over it. This is a problem in which you want to find maximum dissipation. So maximize dissipativity over the choices of input. Dissipativity is defined as this integral, etc. But let me skip that in the interest of time. We have a few minutes left, and I'll do some conclusions on future work. So basically what we did is that for a broad family of control design problems that all have this property that they have a convex parameterization, policy gradient descent converges to the global optimal despite the non-convexity. And by the way, it wasn't enough that there was just the convex parameterization, but the mapping between the convex and non-convex had to be nice as well. In that case, we have global optimality, and also rates of convergence can be obtained in terms of the constants that depend on the problem and instance. And that this goes beyond linear quadratic regulator, and you can see like as complicated as the jump system or H infinity problem can also be handled. And one way to think of all these problems in a unified way was to connect it to the convex problem, instead of directly showing in the non-convex space that, constructing a proof that shows the PL property, you can do this thing of going to the convex space and coming back sort of thing, which makes it much more of a systematic proof. And also it's hopeful because there exist a lot of these problems in control theory where the convex formulation is also known. So in particular, for example, there are whole books about it. There's a book by Boyd and Barrett from 1991 that lists a whole set of control design problems that have a convex form. There's another book of Boyd et al. That lists from 1994 that also lists a range of problems that have, it's called LMIs in control, or linear matrix inequalities in control. So there's a lot of problems that do have a convex reformulation as an STP, as a semi-definite program. So basically, this opens the door to making use of those known knowledge from control theory. So then PL property follows from the convex form and the properties of the map between the two spaces. And there's room to actually make this more precise and more general. The version that I showed you is the one we have now, but there's room to make it better. Yes, question?
So a high-level question. You have a non-convex problem, has a convex reformulation, and then because of that it converges and all. And you analyze the rate of convergence in the non-convex world. So is it any better than the rates that you would obtain in the convex world if you go and solve your reformulation?
It depends, I guess, how you solve the convex problem. In this case, it was a semi-definite program, so it depends on, you can't just do gradient descent ideas. You have to worry about the positive semi-definite cone and so on. But I don't know, maybe not necessarily, it depends.
But the iteration will be more expensive.
Yeah, exactly, exactly. You're solving a semi-definite program, and here you're just taking gradient steps. So it's hard to compare rates, but yeah, computational cost is definitely higher in the STP. Right, so then, yeah, similar methods that are very close to gradient methods can also be handled. I keep mentioning this natural policy gradients because people in reinforcement learning are very interested in that. It's a method that they observe works well. It's just a gradient, but just a matrix that captures the covariance of the state up until that point shows up in front of the gradient. Analysis extends to that as well. And yeah, this is also interesting to look at the derivative-free versions in more detail, but at least as a first cut, it's possible to use very simple derivative-free methods to, after you understand the gradient method, to look at derivative-free versions. So a few directions of future work. One that I'm actually quite excited about is the linear quadratic Gaussian problem. This is a problem where you have still linear dynamics, quadratic cost, but only partial state observations. You do not have the full information about the xt state vector. And that partial observation makes the problem significantly harder. Still in control theory, this is studied. However, the optimal controller in this case is itself dynamic. So there's no fixed k that gives you the optimal relation between the x and the u. But basically, the optimal controller between x and u is itself a system, an ABCD system. So one has to then solve for these dynamic controllers, but there's some partial progress here, and we're also working on it. Actually, there exist some papers that by a group of Noah Lee and collaborators in which there are some negative results. Like this problem seems significantly harder. They did show, for example, that there are saddle points and many, many saddle points, etc. So the loss is not as nice as LQR, but there's still possible to make some progress. But it's still working. Yeah, there's still things open about it. And more generally, whenever you have to design dynamic controllers, it's a much more complicated problem. There are also issues about how do you even parameterize these controllers before you do optimization over in what parameters. There's hope to get better convergence rates on specific problems. For example, those constants in front are not optimized at all. You can probably use better structure of the problem to get the constant in the rate to improve. And finally, perhaps better control theoretic interpretation of these constants. If you show it to a control theorist, they will be like, why do you have all these terms? So there is some connections between things like the minimum eigenvalue of the Gramian matrix and things like that that are showing up in these rates. But they can be made more precise and better interpretation. And yeah, these are the references. So with that, I'll stop here. Happy to answer any questions.
Thank you very much.
Yes.
Thank you so much for the nice talk. So I was wondering if you've implemented any of your methods and if you can talk about like how they behave in practice.
So the gradient method is super easy to kind of implement because you just take gradient steps. We did it on a tiny example that I was showing here, which does clearly show the linear convergence rate. So this is with exact gradients. With exact gradients, it's easy to work. Now, if you're asking about zeroth order with samples of functions, we did a little bit of experimentation, but there's much room to actually explore that more. For a different problem, that looks something like this. This is again another example of continuous time and discrete time LQR. Again, this very nice convergence. That's an example of the zeroth order one, if you wanted to see details, but yeah. And that's, the zeroth order is of course not as smooth. But they were all very simple examples. So we didn't really like go to any complicated robotic problem or they have not implemented it. These are like simple synthetic matrices. Yeah.
Thank you.
Yes.
So if you use, neural net for policy parameterization, is there any hope in doing something like this?
That's a good question. Actually, that's the actual motivation to start from, because what people do in reinforcement learning is exactly that. They parameterize the policy with a very complicated neural net with a lot of parameters. So at first, it seems like it's going to be very hard, but perhaps if one starts with very simple parameterization at first and slowly makes it more complicated, then you can start to talk about derivatives or gradients with respect to those parameters.
Right.
So like 2-layer network, only one nonlinear layer, etc. Things like that, there is hope.
How do you evaluate the gradient of your loss function with respect to your feedback matrix K?
Yeah, that's a good question. So we assume there was an oracle that gives you the value of the gradient of the loss. And in practice, you sometimes need to know the full model to evaluate it if you want to evaluate exact gradient. So it's a little bit of idealization for the analysis. But the zeroth order evaluation is much more realistic. You can actually do that by, I just briefly mentioned that. Right, so this kind of approach can be implemented, which means that I do not get the gradient. What the oracle I call is the following. I am running a policy, and then I actually, at that point, at that policy, I'm going to perturb a little bit, like your robot is going to move around just a little bit and collect data, basically, to see what happened to its cost. Like I moved a little bit in that direction, cost went up a lot. Okay, another round, and then you pick these directions randomly. So you pick a certain number of random directions, move a little bit, collect the loss values from those points, and then use that to construct an estimate of the gradient, then move in that direction. But that's very, very simple kind of zeroth order method. One can actually say convergence still overall happens. You need to quantify exactly how long you would do this exploration for, and how many overall samples, how many overall directions you need to check. But they can be written out. So the numbers of samples becomes pretty large. But at least it shows that it's not too far off from the practical thing. What question here?
Yeah, do you know if this is just true universally, that whenever you have PL inequality, you have a equal and convex parameterization?
No, not the other way, not necessarily.
You have negative examples, or we don't know?
We don't know. Yes?
Yeah, I wanted to ask a little more about the PL inequality and how you could show that. So I'm sort of thinking about there are various convergence results for non-convex problems, right? Like for example, for stochastic gradient descent, like one of the things you'd need is you'd need the expected gradient to be Lipschitz continuous, right? So in the work you just presented, it's very interesting to me because I've never heard of this PL inequality before. So what I'm sort of wondering is what exactly do you need to show this PL inequality? So you kind of mentioned it, like it seemed like you're saying you need this convex mapping, or yeah, does that make sense? Could you?
Well, so either you can try to, for your problem, directly prove a PL property without going to the convex domain. You can try that. Actually, that's how first we did it for the LQR problem. For most problems, it's not going to hold. It's a very, very strong property. But just magically for these control problems, it holds. So it tells you that these problems are superstructured. So it's not something that's going to be very general. But it's interesting that like 5 different control problems of increasing complexity still satisfied it. But for example, that LQG problem does not satisfy it. So there are also a lot of problems that don't satisfy. We don't have any knowledge of what gradient descent does in those. The view to convexity is, I think, quite interesting because it basically says that if there exists another parameterization of the problem that is convex, then you would think that would, maybe that solves the problem. It's not enough. If that exists, such a convex parameterization, and also the parameters in the convex domain have a nice mapping to the non-convex domain, so you can actually go back. So if you give this L and G in the non-convex domain, I can construct a K that is LG inverse. If such a relation exists, then you can conclude PL in the K domain. So you see, actually, it's like relying on a lot of pieces. It's not as, and we don't expect it. It's a very strong property. It's not going to hold like just out of nowhere. Yeah, sir.
Is something like a Euler parameterization, does that not satisfy the kind of bidirectional type property, or is that something that could?
I think it actually could. I haven't looked into details because that's very general. Euler parameterization is like transfer function parameterization. So yeah, it's a good one to explore.
So maybe we should take all the other questions offline. As in the usual CAM tradition, there will be refreshments up on the 6th floor. So if everyone wants to return upstairs, can ask the questions informally. Thank you very much.
Thank you.